Hello everyone, my name is Lila Serrahis and I'm a postdoctoral associate at NYUAD. I'll be giving a short introductory presentation to the exciting field of graph neural networks and how we have used it for hardware security. So the motivation why we study graphs is that circuits can naturally lend themselves to graph representations. You can see the circuit here on the left, it is nicely captured as a graph on the right. Gates are connected by wires in the circuit, and these are represented as nodes and edges in the graph. So once we have the circuit represented as a graph, now we can ask ourselves some interesting questions about the circuit, whether the circuit contains malicious hardware, for example, or not. When learning on the graph, we will need to do feature engineering. We want to take the network and represent the nodes by a set of features and obtain a set of structured data. Then we can apply some learning algorithm and build a model to solve for a specific task. And we like to skip the step of feature engineering and automatically represent the circuit by an embedding that captures its properties, which can then be passed to the downstream task. So this is an example. We would have a network and we wish to obtain an embedding vector for each node in this graph that will capture its properties. And this is helpful for different types of networks. It is used in protein-to-protein interaction graphs and in social networks, in addition to circuits. Now, to implement this task-independent embedding generation, we use graph neural networks, GNNs. And in a GNN, to get the embedding of a node, we will start with its own features, and then the node will get information from its neighbors, where its neighbors obtained information from their neighbors. So at the end, we will get an embedding for each node that will capture its properties, the properties of its neighbors, and the structure of the graph. So we started with a network and a feature matrix where each node in this network was associated with a feature vector that captures its initial properties. These were fed to the GNN, and the GNN was able to construct an embedding matrix that can be used for different classification tasks. So we can use the generated embeddings for node classification tasks, for subgraph classification tasks, or link prediction. So for node classification, we are interested in the properties of the nodes themselves. And in subgraph or graph classification, we are interested in the properties of all of the nodes in the subgraph in the graph. So we're looking at the overall graph structure. And in link prediction, we learn the link formation in this network. So for us, we use GNNs in different hardware security systems. For example, GNN-RE, where we use the GNN to perform reverse engineering of gate-level netlists. If we look at a reverse engineered netlist, we will obtain a sea of gates, and it is difficult to identify the subcircuits that exist in this netlist, and it is difficult to understand the functionality of this design. So to get this information, we convert the netlist to a graph, and we extract a feature vector for each node in this graph. So basically, we extract features regarding the gates in the netlist, and this information will be fed to our GNN model that will tell us specifically which subcircuit each gate belongs to. So we will be able to identify the subcircuits that exist in this netlist. We'll be able to see the connections between them and figure out the design, the functionality of the design. Another application is GNN-Unlock, where we use GNNs to evaluate the security promises of the design for trust solution logic locking. In logic locking, the circuits are locked to protect them from IP piracy and overproduction. And the idea is that the circuit will not operate correctly unless a secret key, or we can refer to it as a password, is fed to this circuit. So the circuit will be modified so that it will basically produce invalid outputs for an invalid key. And in this specific implementation, these built-in errors, let's say, are implemented using two units, the perturb and the restore unit. And if we look at this implementation, if the attacker is able to figure out where is the perturb unit and the restore unit is implemented within the circuit, they can remove those and obtain the original circuit without any errors. And this is what we do in GNN-Unlock. We represent the circuit as a graph, and what we have noticed is that these perturb and restore units, so basically these protection blocks, they have some specific properties. And while studying the properties at the graph representation, we are able to differentiate between these different blocks. And just to show you how helpful the GNN is, here we are visualizing the features of the nodes for these different blocks, and we're showing the classes. And you can see now that it is difficult to identify the perturb nodes. We cannot really see the blue nodes in this representation. So these are the features before feeding them to the GNN, and it is difficult to identify the perturb block. However, after we process the network using the GNN and we obtain the final embeddings, you will see now that we have clear clusters, and it is easy to actually identify the perturb and the restore blocks and figure out where is the original circuit located. OMLA is another GNN-based platform that we have developed to study the security of logic locking. And using OMLA, we are able to identify vulnerabilities in the traditional implementation of logic locking. So in the traditional implementation of logic locking, there is leakage in the circuit itself that tells us about the secret key that controls this circuitry. So what you can see here on the right, we are highlighting in red some gates that actually capture information regarding the secret key. And if we're able to learn on the circuitry surrounding a key gate, so this key gate is the newly added gate that is controlled by a key. If we're able to learn on the circuitry, we will be able to figure out the correct key bit value. So to do that, we convert this circuitry to a graph, and we extract some features regarding the gates in this circuitry, and we feed that to a GNN. And the GNN will actually give us an embedding for this subgraph that we are interested in. And then based on this embedding, we are able to figure out the key bit value. So in this task, we are looking at the subgraph level, and we're able to capture information or basically learn information on subgraphs that will help us to figure out the secret key bit. UNTANGLE is another interesting GNN-based platform that we have developed to assess the security of logic locking. So again, there are different ways to implement logic locking, and in one of the implementations, the connections in the circuit are obfuscated. And for us as attackers, it is difficult for us to figure out the correct connections in the circuit. So what we do is we convert the circuit to a graph, and we mark all of these obfuscated links as target links. And our goal is to identify which of these links are correct. So to do that, we solve this using a link prediction platform. And in a link prediction problem, the idea is that given an incomplete network, predict whether two nodes are likely to have a link. And this is what we do. We take an incomplete circuit and we predict whether two gates are likely to have a connection or not. So we solve this using a GNN. So once we get the graph representation of the circuit, and let's say we want to figure out if there's a link between gates A and B, what we do is we capture a subgraph around these target gates A and B, and we feed that to the GNN. The GNN is going to learn on the properties of these target gates, the properties of the surrounding nodes, and the structure of the graph. And it will be able to give us a link representation that can capture the properties of the link. And we use this embedding to classify whether the link exists or not. With that, we have come to the end of our introductory video. This is the list of related publications. If you are interested, you can check out our papers, and feel free to contact us if you have any questions or if you would like to know more regarding what we do.